Good afternoon or good morning, everybody, wherever you might be. It is my pleasure to welcome my friend and co-author, Francesco D'Andrea, who will tell us everything and more about the notion of a non-commutative submanifold. Francesco, it's all yours. Take it away.
Thank you very much, Piotr. Okay, so let me see if it works. It's the first presentation on Zoom. We use Teams usually. Okay, let me start with references. So this talk is based on a recent paper with the same title on the notion of non-commutative submanifold. And the motivation is from some quite old, I would say, papers by Michel Dubois-Violette and by Thierry Masson. These are the paper I'm talking about. In 96, so 25 years ago, Thierry introduced this notion of submanifold algebra as a possible candidate for what should be the analog of a submanifold in the non-commutative world. And the definition was motivated by the so-called derivation-based, let's say, approach to non-commutative geometry of Michel Dubois-Violette, and I'm going to recall briefly what it is, how it works. Okay, and what I want to do today is I will give a review of some of these definitions, of some basic properties, present some both commutative and non-commutative examples and counterexamples. The definition, I will arrive immediately to the definition of submanifold algebra is something quite natural that actually people have been studying under, let's say, different names. So there is a different approach to non-commutative submanifolds that is more in the direction of Riemannian geometry, so that you can find in this paper, a recent paper by Arlind and Norquist. So this is a different notion because you have, I mean, there is some kind of Riemannian metric involved, and you have something analog to not just embedding, but isometric embedding, something like that. So, okay, so the plan of the talk is the following. First, I want to start with some basic definitions and explain some basic properties of submanifold algebras. Then I will pass to commutative examples. So the first thing, when you have let's say, non-commutative generalization of some classical geometric notion, I mean, the first question is, what do you get in the commutative case? So here the question is if every commutative, non-commutative submanifold is a submanifold, but I mean, like every commutative compact quantum group is a group. So one would like to understand if something similar holds. I will pass to non-commutative, both examples and counterexamples. And then to formal deformations. And for formal deformations, here is where you can prove some obstruction theorems. I mean,
sorry, Francesco, just to be on the same page. I understand that the examples and counterexamples will not be for the same theorem.
Well, examples, I mean, example of submanifold algebras, and counterexample actually later are called non-examples. Non-examples meaning that they are objects that are quotient algebras, but not submanifold algebras. I will come back to this, what I mean by non-example later. Not counterexamples to theorem that I proved. This, yes, of course. And okay. So just to fix the notations, by smooth manifold, I mean standard ones. So I have no boundary. They are Hausdorff second countable, finite dimensional, of course, and they may not be compact. I'm not assuming that they are compact. Continuous functions will be complex valued for some reason, because we like to work with complex C-star algebras. And real functions, and sorry, smooth functions will be real valued, because this is what we use usually in differential geometry. But I mean, if you replace them by complex functions, it's the same, everything works. This is just to fix the notation. So infinity of M for me will be the algebra of a real valued smooth function on a standard smooth manifold. Okay, So what is this derivation-based approach to non-commutative geometry? I have a lot of things popping up on my screen. I hope they are not covering the slides. They are covering my slides on the screen, but okay. So let me know if you cannot read for some reason. Okay, suppose you have an associative algebra A. Then given an associative algebra, you may want to associate to it a differential graded algebra, what we call the differential calculus. There are several ways to do it. We know that you can use Dirac operators, you can take the universal differential calculus and so on. And there is one differential graded algebra that is really close to the algebra of differential forms in the case of manifolds. So to construct this, we just imitate, let's say, imitate what happens when A is given by smooth functions on a manifold. Then we can use derivations of the algebra as vector fields. By derivation here, I mean maps from A to A, so with trivial coefficients, let's say. We can use these as vector fields because this is what they are classically. And we can define dually forms. So one forms will be module maps from derivations to the algebra itself. And by module map here, so derivations, they form a module over the center of the algebra. So by module map, I mean linear over the center of A. Higher degree forms you define in a similar way. You take antisymmetric multilinear maps, and I didn't write down the formula, but I mean, you know how they are defined classically, and here we do the same. You just replace, instead of having linearity over A, you have linearity over the center of the algebra. And then you can do, basically, you can generalize all the structure that you have for forms on a manifold. You have your exterior product. And since A is non-commutative, zero forms are just elements of the algebra. Since A is non-commutative, the exterior product will not be graded commutative, but okay. You can define the exterior derivative using Chevalier-Eilenberg formula. And here is I wrote down just the case of zero forms. So if A is an element of the algebra, X is a derivation. So let's say a vector field. The differential of A evaluated at X, this is just X acting on A. So this is quite natural. Now, inside this differential graded algebra, you can consider the smallest differential graded subalgebra that contains A, and this will be generated by A and by differentials of elements of the algebra. And this is what is called usually minimal derivation-based differential calculus. Okay. Now, the next step is suppose you have a quotient algebra B. So B is a quotient algebra of A. And if we want to give a geometric interpretation, we could say, okay, so B is describes of some kind of non-commutative subspace. So if these are sister algebras, commutative sister algebras, so a quotient algebra is dual to the notion of a closed topological subspace. So let's say that you have some kind of non-commutative subspace. Well, if this is a submanifold, then you can take vector fields and you can restrict them to, you can take differential forms and you can restrict them to submanifold. The pullback is via the inclusion is always well defined. And so we wonder, okay, if it is possible to do the same in general. So given called pi, the quotient map from A to B, so quotient map means it is a surjective homomorphism of algebras. Can we extend this quotient map under the sole condition that it is surjective to a DGA map from one differential calculus to the other? And here is the minimal one, the one that we consider. So let's say when this extension is well defined. Well, clearly, if you want to this map to commute, DGA map means that it commutes with the exterior derivative. So the differential of A of an element of the algebra should go to the differential of pi of A. This is well defined is if the map pi sends the kernel of D into the kernel of D. And you can write down what this means. So this means that if the dA is equal to 0, then any derivation of B applied to pi of A should give you 0. This is the condition for this map to be well defined. There is an obvious sufficient condition. If you can move y on the right of pi, then this will be automatically 0. What do I mean by moving y to the right of pi? So if there exists a derivation x of A such that pi x is equal to y pi, then what is written here is just pi applied to the differential of A evaluated at x, but this is 0 because the A is 0. So a sufficient condition to be able to push forward your differential forms is that every derivation of the algebra B can be lifted to a derivation of the algebra A, whereby can be lifted, I mean this property here. There is an X satisfying this condition. And we arrive to the idea, to the notion of submanifold algebra. So the short definition is given a quotient algebra B of an algebra A, if B is a quotient algebra of A, we will say that it is a submanifold algebra if every derivation of B can be lifted to the big algebra A. Okay, we can say something more, introduce some more notation because I'm going to need it later. So suppose pi is, as before, is a surjective algebra morphism, call J the kernel. Then then you can consider those derivations of the algebra A that send the ideal to itself, so such that X applied to the ideal J is still in the ideal J. And I use this notation for this set. This is not the same notation of a theory paper, but okay. I denote it by there with a pi below. So you can think of this as the set of derivations that you can push forward to B, in the sense that if X belongs to this set, then you can, there is a unique, well-defined derivation of B, let's say Y, defined by Y acting on pi of A is given by pi applied to X of A. So this is well defined if this condition of compatibility with the ideal is satisfied. These are the derivations that you can push forward in some sense. And you have a map, so the association to X, to such an X of such a Y, this gives you a map that I denote with pi and a star below, from these projectable derivations to derivations of B. And okay, so now you can rephrase this definition, this notion of submanifold algebra. You can say that if pi star is surjective, so if every derivation of B is in the image of this kind of push forward, then B is called a submanifold algebra. And I will also call pi a co-embedding. I want to give a name to the map, not only to the algebra B itself, because I'm going to refer to it. So what was the main motivation to introduce this notion of submanifold algebra? This was, I mean, the main motivation is the example of closed embedded submanifold. So if S and M are smooth manifolds and I from S to M is a proper smooth embedding, I mean a smooth embedding and a proper map, then you can call pi the pullback of this I, and the pullback is surjective, not only surjective, but is a co-embedding. So every vector field can be extended from a closed smooth submanifold to the whole manifold M. So this is the, say, the commutative, main commutative example. And of course, one may wonder if that's all, even in the commutative case, if this is all we have to say about these submanifold algebras, or there is something else. Okay, so just to repeat, the reason why I called this pi eco-embedding is simply because it's a dual, in some sense, is some kind of dual smooth embedding. Okay. So there are several questions that one may ask that are quite natural. So, well, first of all, what are really these submanifold algebras? So for what classes of quotient algebras there are theorem, we can say that all derivations can be lifted. This is something that people have been studying, of course, and is completely independent of its interest in non-commutative geometry. So what are the classes of quotient algebras B of A such that you can lift all the derivations? Or can we give some kind of geometric or non-commutative geometry interpretation to this property? I mean, can we give sufficient conditions and so on? Another question is these co-embeddings, they are morphisms in the sense that you can compose two co-embeddings and still you get a co-embedding. So one may wonder what are the categorical properties. I will say I only have one remark on this. There is not much I have to say. And okay. And then there are questions about the commutative case. So you can focus on exact sequences of commutative associative algebras. And
sorry, Francesco, there is a question.
Yes.
It's written in chat.
Okay, sorry, I cannot see the chat because
I'll read it for you. I'll read it for you.
Yes, thanks.
But in manifold case, the lifting is not unique compared to the uniqueness in algebraic definition. Am I mistaken?
No, the lift, I would say that is never unique. The lift of a derivation. No, it is not the lift. Sorry, let me come back. It's not the lift that is unique. It's the opposite. I mean, if I have a derivation of A, where is it? Yes, here. So yeah, if I have a projectable derivation of A, then is a push forward to B is unique. So let's say that B is a submanifold and A is the big manifold. This means that if some vector fields can be restricted to the submanifold, and the restriction is unique, but the opposite is not true. If you know the vector field on the submanifold, the lift will not be unique even if it exists.
Yeah, that's clear.
Okay, so this is, I mean, this map by star will not be injective, almost never injective. What I'm wondering if it is surjective. It won't be injective.
Property. I agree. Is every vector field liftable?
Yes, okay, so yeah, so a special case is when the big algebra in the middle A is given by smooth functions on a manifold. And also here, there are several natural questions. So for example, in the commutative case, and by commutative case, I mean this. So you have infinity of M, some ideal and some quotient algebra B. So can we find an example where pi is surjective, but pi star is not? So these two conditions, are they independent from each other, or one implies the other in the commutative case? Is there an example where they are both surjective? So you have a submanifold algebra, but this submanifold algebra is not given by smooth functions on a manifold. So is this notion of submanifold algebra already in the commutative case more general than the notion of embedded submanifold, let's say? We can ask more. We can assume that J is the vanishing ideal of a subset of our manifold M. B is the corresponding quotient algebra. So if B is a submanifold algebra, so has this property that all derivations can be lifted. If B is a submanifold algebra, does it mean that S is a submanifold of M? And then there is one more question. I will answer to this question today. So, but first I want to read them all. And the last question is, okay, and what if we assume that B is given by smooth function on a second manifold? Then what can we say about this special particular case? Okay. So what I want to do is before discussing these questions about the commutative case, let me start with some initial properties of submanifold algebras. These are observations, results that are already in Thierry's paper, and in particular this part about inner derivations. So, okay, I don't have to recall you the, the definition of inner derivation. The observation, important observation is that if you have a surjective algebra morphism pi, so from A to B, and you take an inner derivation of A, every inner derivation is projectable since our ideal J is indeed an ideal. If you take the commutator with something, you still are inside the J. So all inner derivation can be projected. The projection is still an inner derivation of B, and this map is actually surjective. So pi star is always surjective on inner derivations. So this gives us immediately a class of examples of submanifold algebras. And whenever B has only inner derivations, then it is a submanifold algebra. So any quotient algebra with only inner derivations is a submanifold algebra. So this is, I mean, this is a simple, an immediate property, but still there are quite a lot of examples where this happens. So what are the algebras with only inner derivations? Well, we have the universal enveloping algebra of some kind of Lie algebra G, semi-simple, finite dimensional. You have a central simple algebras. So these are simple algebras, meaning with non-trivial ideals. So central means that the center is trivial. While algebras, and I wrote down the canonical commutational relations just in case there is some physicist following. So while algebras, it is well known that they only have inner derivations, von Neumann algebras, and as a special case of this last but one point, well, finite dimensional, real or complex sister algebras, they only have inner derivations. So what is, for example, one finite dimensional sister algebra that we like? Well, one that I like is C plus quaternions plus M3C. So this is the one of the standard model. And in general, suppose you have, for example, an almost commutative space, meaning an algebra of functions on a manifold, which is matrix valued, so with values in matrices. Then you can evaluate this function on a point. You have a projection, you have a quotient map from almost commutative space to matrices. And this is a case where you have a co-embedding for this reason, that all the derivations of the quotient algebra are in. So a fancy way to say it is that in an almost commutative space, manifold, or from the algebraic point of view, if you have some kind of algebra bundle where fibers are finite dimensional sister algebras, well, the fibers are non-commutative submanifolds in the sense we are talking about. So these are the simple examples. I mean, simple because, I mean, it is immediate that they are submanifold algebras, but of course, there are some quite complicated theorem here that, okay. Okay, the next, in particular, so a class of example is given by finite dimensional sister algebra. So the next question is, okay, what happens if you have a sister algebra which is not finite dimensional? And again, this is a question that was asked long before the idea of submanifold algebras. And so let me tell you what happens. So also here, a lot of things are known, more or less everything is known. So if your exact sequence is a short exact sequence is an exact sequence of sister algebras, so what can we say? Well, first of all, every derivation of A is not exactly inner in A, but is inner in the double commutant, because we said that, I mean, this is still a Sakai-Edison theorem. And from this, one can prove, this is in a paper, older paper by Pedersen. From this, one can prove that even if its derivations are not exactly inner, still it is true that because of this property, that they send, they map the ideal J to itself. So every derivation of A is projectable. They can all be projected to B. And the question, of course, is when is the opposite true? So when this map pi star is surjective, the answer is not always. There are counterexamples. There are some famous counterexample where you have a quotient sister algebra and derivations that cannot be lifted. but they can be lifted at least in the separable case. So if A and B are separable, okay, then everything is fine. So in particular, what happens for commutative sister algebras here? Well, I mean, every short exact sequence is equivalent to one like this, where M and N are locally compact Hausdorff topological spaces. And for commutative sister algebras, of course, all derivations are zero, and this is something quite easy to prove. And in particular, pi star is surjective for trivial reason, because I mean, it is the zero map, but it is still surjective. So every quotient map of commutative sister algebras is a co-embedding, and in the case of commutative sister algebras, that is, in the case of topological spaces, a non-commutative submanifold is just a closed topological subspace. So as usual, at topological level, everything is nicer. I mean, here the notion of submanifold algebra is equivalent to the one of, for trivial reason, to the one of topological subspace closed. And if we pass to from continuous to smooth functions, this is of course things get a bit more complicated. Okay, so let's move on and pass to the case where we have a short exact sequence of commutative sister algebras, and the one in the middle now, sorry, not sister algebras, of commutative algebras, and the one in the middle is the algebra of smooth functions on a manifold. You can assume that the dimension is greater or equal than 1, otherwise all vector fields are 0 and there is nothing to do. And so what about this example? Let me recall, so let's see one by one these questions that I mentioned, even if here I think they are in a different order, these 4 questions. So the first question is, well, is every submanifold algebra a submanifold? I mean, if B is a submanifold algebra, is B isomorphic to smooth function on a manifold N, or can we find counterexamples? Well, there are counterexamples. I mean, there are a lot of nice counterexamples. One is given by dual numbers. So as quotient algebra, you consider polynomial in epsilon quotiented by epsilon square. And here you can put every manifold, but I put the real line just to keep things simple. And you can define pi, consider the following map, the map sending a function f to f of 0 plus f prime 0 epsilon, where this is the first derivative. Then you can write down everything, compute what are the projectable derivations and so on. Well, projectable derivations, these are just the derivations that are vanishing at 0, at the origin. Well, derivations of the algebra of dual numbers, these are generated by this kind of Euler vector field, if you want to call it like this. They are scalar multiples of this. And immediately you realize that pi star is surjective because this Euler vector field is in the image of this map, is the image of this vector field on the real line. This is an example where J is not the vanishing ideal of a subset of your manifold. And is also an example, so it is an example of submanifold algebra, commutative submanifold algebra, not given by smooth function on any manifold N. And this you can prove by, I mean, by simple argument, because you have non-zero nilpotent element, and which could not be possible if it were some algebra of smooth function or of functions on a set. Okay, so this is the first counterexample. Another example of submanifold algebra, which is not just a submanifold or any manifold, is given by germs of smooth functions. Also here, I mean, here everything is quite trivial, everything is well known. So take a point in your manifold M, take the map sending a function into its germ at P. Well, this is of course surjective. So the one on the right is a quotient algebra of the one on the left. And it's not difficult to realize that it is also a co-embedding because, well, derivations of the quotient algebra, these are tangent vectors at P. the map pi star is the one sending a vector field to its value at p at that point. This is, we know that it is surjective. Every tangent vector can be extended to a vector field. And then you have eco-embedding. It's not isomorphic to any algebra smooth function on a manifold for trivial reasons, since by contradiction, you would get a manifold whose vector space of vector fields is finite dimensional and not zero, which is not possible. And it is another example where J is not the vanishing ideal of any subset of your manifold, but it is close. So J is the ideal of functions that are zero, not at P, but near the point P. Okay, so second question. Now, assume now that J is the vanishing ideal of a subset of your manifold. Assume that the quotient algebra B is a submanifold algebra. Then is S a submanifold of M? Can we conclude that it is a submanifold? And here the answer is negative. So we can do the following construction. I will denote by C infinity of S with a circle, the set of real valued functions on the set S that have a smooth prolongation to an open neighborhood of S in M. The standard notation would be without circle. I put a circle because if S is an embedded submanifold, a closed embedded submanifold, then these are just smooth functions on S. But there are other cases, for example, already for immersed submanifolds, this is not the algebra of smooth functions, it's something else. Oh, I mean, it can be the same, but it can be different. Okay, now if S is closed, I mean, there is an obvious map from C infinity of M to this algebra C infinity S circle, the map given by the restriction of a function to S. And this map, if S is closed, it is surjective, of course, but not only that, it is actually a co-embedding. And now, since I'm going quite slow, I'm going to skip the proof, but it's something, some elementary differential geometry. So this is an example. If F is any subset of a smooth manifold M, S in this sense is I mean, closed subsets are non-commutative submanifolds in this sense. You have a natural, an obvious co-embedding associated. So let me skip something.
By the way, about going slow, you used about 1/3 of your time and 10 out of 25 of your slides. So it's not so slow. I mean,
okay, so maybe let me explain, give some hint of the proof. I mean, the last part I think is, it would take more time, but okay. In any case, this is, I mean, I'm not even sure that it is interesting to give proofs in this seminar, but I mean, the proof is simple because, I mean, it's basic differential geometry. If S is closed, you can use basic argument with cutoff function to show that any function here can be extended to the whole M instead than just an open neighborhood. So the map pi is surjective. Then you can realize that if X is a derivation of the quotient algebra, if you compose it with pi on the right and with the evaluation at the point P on the left, well, this is a derivation at P of your smooth functions on M, so it is a tangent vector. And then you can write down, I mean, you can write this tangent vector in a chart. You choose local coordinates around P. Let's say that P is a point of S fixed. Choose local coordinates. Choose a coordinate ball containing P such that the closure is in the chart, and write down the local expression of your vector field. We don't know if it is smooth. And this is what we want to see. Well, how do you prove it is smooth and it has indeed a smooth prolongation to the whole M? Well, choose a smooth prolongation of your local coordinates. X acting on these functions, this is a map, an element in the quotient algebra, but pi is surjective. So these elements in the quotient algebra are pi of some smooth functions on M. Then you take these smooth functions and define a new vector field that I call y, given by fij over the x. This is not global, still is defined only on your chart, but in this coordinate ball, it coincided with x. So what is that we proved? We proved that locally, around any point, a derivation of the quotient algebra can be extended to is the restriction of a local smooth vector field on M. So this is what we call vector field, I think, on M along S, along the subset S. It is known that this kind of vector fields can then be extended to the whole M, and this is the standard theorem. And then you're done. You proved in this way that pi star is surjective. Okay, so I mean, even if you assume that J is the vanishing ideal of a subset of M, and your quotient algebra is a submanifold algebra, this doesn't mean that you have a submanifold. S can be any closed subset. Okay, the next question is, okay, since it is quite a general, this notion already in the commutative case, but maybe every quotient algebra is a submanifold algebra. Maybe at least in the commutative case, at least when A is the algebra of smooth functions of the manifold, every derivation can be lifted. So do we have counterexamples? So let me produce some an elementary counterexample. An elementary counterexample is the following. Actually, here the big algebra is given now not by smooth function on a manifold, but by smooth functions on a subset of a manifold. So, I mean, the question whether you have a counterexample where the algebra in the middle is a smooth function on a standard manifold is actually, I could not find a counterexample of that type. So anyway, so commutative counterexample, take S the union of the two axes in R2, so the cross, the standard cross, and consider as a subset the real line, the horizontal line. Say you have a map I sending a real number X to the pair X0, and pi is the pullback of this kind of inclusion, of this injective map. So pi is a restriction of a smooth functions on the cross to a smooth function on the horizontal axis. Then you can use previous theorem. From previous theorem, we know that every derivation of this algebra of smooth function is the restriction of some kind of vector field on R2. And if you do the computation, you will find that this vector field should have components. The first one vanishing on the y-axis, so for x equal to 0, and the second one vanishing on the on the x-axis, so for y equal to 0. In particular, both components vanish at 0. So every derivation of these smooth functions on the cross, they are 0 at the origin, the double point, so the tricky point, let's say, of this set. You can project a derivation if it is projectable, and realize that any derivation in the image of this pi star should vanish at 0. So use a vector field on the line vanishing at 0, meaning that in particular pi star is not surjective. So this is an example of commutative quotient algebra that is not a submanifold algebra. And the trick here is that in the big algebra, we have a double point. We have a set with a double point, and the subset, the real line that we consider when we do this projection, this double point becomes single, let's say a standard point. Okay, this example allows me also to give a remark about categorical properties of co-embeddings. So suppose, let's start from the commutative case. Suppose you have two smooth maps alpha and beta between manifolds. Let's say you have three manifolds M and P and two maps alpha and beta that you can compose. Now it is known that if the composition is a closed embedding, that this implies that alpha is an embedding. So this is quite a strong property of embeddings. The analog property of for co-embeddings is not true, the dual property. What is the dual property? I mean, I give you immediately the counterexample. Consider the following sequence of quotient maps of commutative algebras. You start with R2 smooth functions. Here in the middle you have the cross, so F is the restriction what was called the pi before. Here I cannot use everywhere pi. So the first map is the restriction of functions on R2 to the cross. The second map is the restriction of functions on the cross to the horizontal axis. So we saw that F is a co-embedding. The composition also is a co-embedding because the horizontal line is an embedded submanifold of R2. Still, even if F and the composition are co-embeddings, G is not a co-embedding. So this nice categorical property of embeddings is no longer true for, I mean, at dual level, at the algebraic level. Okay. Last question, and then we pass to non-commutative examples. Last question is, what if we assume that also the quotient algebra is given by smooth functions on a manifold? What can we conclude in this case? And here, I mean, the answer is probably something everybody would expect. So the conclusion is that N must be a submanifold. So suppose the theorem is the following: M and N are smooth manifold. Pi is a surjective homomorphism of commutative associative unital algebras. And then, so this is the hypothesis. The thesis
Sorry, why
is that,
unital? Do you assume compactness?
No, these are smooth functions. They don't vanish at infinity. They can be unbounded.
Okay.
So, I mean, I'm not working yet with operators, with bounded operators, so I don't care.
Okay,
So,
okay, I've got you.
And I'm doing this because, I mean, simply because in differential geometry you use this. I don't know if some theorems have an analog with functions vanishing at infinity.
True, yeah.
And okay, so if pi is a quotient map, is a surjective homomorphism, so what we can conclude is that it is the pullback of a proper embedding of n into m, and in particular that S, if you call S the image of n through f, this is a closed embedded submanifold. So in particular, the condition on pi star is not necessary. Surjectivity of pi implies surjectivity of pi star. So in this case, just every quotient map in this particular case is a co-embedding. Why is this true? Also, this is a collection of known results. You have just to take several things that are known, then put the pieces together. First of all, whatever is pi, even if it is not surjective, whatever is pi, we know that it must be the pullback of a unique smooth map capital F. So this is, it was not easy actually to find a reference where this is proved, but okay, it is something well known, and if somebody is interested, the references are in my paper. Then you can prove that if pi is surjective, F must be injective, and this is just the property of manifolds that you can separate points with smooth functions. Using this property, you prove by the contradiction that is, if capital F is not injective, then the map pi cannot be surjective. Next step, you prove that F is an immersion. And why is F an immersion? They take a point in the manifold N, take any smooth function on N, and compute the differential of F at P. Well, F, you can always write F as pi of some function G on M. Choose any function G, doesn't matter. And so from this, it follows that the differential of F is the differential of G composed with the tangent map of capital F. Now, this implies that the F at P, this is a covector vanishing on the kernel of the tangent map. Since all covectors of this form vanish on this kernel, the kernel must be trivial. So the map capital F is an injective. P is an arbitrary point. So the tangent map is injective and F is an immersion. And now is the last known result. We know that given an immersed submanifold, we know that the restriction of smooth functions to this immersed submanifold, this is surjective if and only if S is properly embedded, and then you are done. So you prove that your capital F is a proper embedding. Okay, so in the commutative case, meaning when you work only with
Sorry,
smooth
Francesco,
functions.
may I just ask a few questions? So a simple example of improper embedding would be like, say, the Kronecker foliation of a torus, right? You have R inside T2, but this is not a proper embedding, right?
Sorry, an example of proper embedding?
Of improper embedding.
Or improper embedding? Well, any open submanifold, I would say. I'll take an open ball.
Closed? Yeah, but what I said was also not closed. Okay, anyway.
Yeah. No, proper embedding implies closed, and I think it's true also the converse. If you have a closed embedded submanifold, then the embedding is proper.
Okay.
So improper must be open if you want a counterexample.
Yeah, okay,
So,
that answers my question.
So the open disk is is
actually
improperly
open
embedded.
Versus closed. Okay, and I'm looking at this theorem, and please correct me if I'm wrong. If I would change my assumptions, if instead of demanding that my target algebra is the smooth algebra functions on some manifold, I would demand that the kernel of such a map, so I'm mapping onto some commutative algebra subjectively, and I assume some properties of a kernel, like, I don't know, that the kernel is the vanishing ideal of a submanifold, of a closed submanifold, then everything would still hold, right?
Well, I mean, if it is a vanishing ideal of a submanifold, yes. If it is because the quotient algebra is isomorphic to smooth functions.
Yeah. So this is just rephrasing these assumptions. Okay.
Yeah, it's just rephrasing this assumption.
Okay.
If you take a vanishing ideal of a closed subset, still this works, but it's a co-embedding, but not a submanifold. Okay. Okay, so I have 45 minutes, so let's say 40. Okay, now maybe I'm going really slow. I mean, you can pass, instead of smooth functions, you can consider polynomial functions. There is a nice reformulation of the notion, if you want, of submanifold algebras in terms of Kähler differentials. But maybe I will skip this part. I want to go fast because I want to arrive to some to the non-commutative part. So, I mean, the interesting point, if you want, is by working with Kähler forms, you can prove that if A is a commutative, is any commutative algebra, and the modulo of Kähler forms is free, then every quotient algebra of A is a submanifold algebra. So, for example, this is a sufficient but not necessary condition, of course. So, for example, you take polynomials in n variables. For this algebra here, it is true, it is known that the modulo of Kähler differential is free. Any quotient algebra of this A is a submanifold algebra. In particular, you can take the ring of the coordinate ring of, I don't know, any affine algebraic set. It's actually much more general, but take the coordinate ring of an algebraic set, and this implies that algebraic sets, whatever they are, even if they are not submanifold, they are non-commutative submanifolds of k to the power n. K, let's say, is any field of characteristic 0. And okay, so let me maybe move on. Let's go to, I want to go fast also on this. Let me give a non-commutative non-example. So an example of non-commutative quotient algebra, which is not a submanifold algebra, so that doesn't have this lifting property of derivations. And I mean, I don't know, for some reason, whenever I see a definition, I have to understand if counterexamples exist. So we know that a commutative counterexample exists, but let's see a non-commutative one. So a non-commutative one is given by the following. You can take as A, this is quite close to the example of the cross, is let's say the non-commutative version of the cross. You can take as A the universal enveloping algebra of the Lie algebra with bases H and D and the commutation relation, the one that you see, HE equal to E. You can take as B polynomials in X, and as quotient map, basically the map sending E to 0. And then working with Peter Weil basis, you can prove it's not difficult to prove that pi star is not surjective on derivation. You can prove this by contradiction by checking that the derivation x day over the x, again, this kind of Euler vector field, this is not in the image of pi star. So this is an example of commutative of quotient algebra, again, which is not a submanifold algebra. And now I don't know who is listening, but now the title I used for this slide was is Kappa-Minkowski, because if you want, you have this folkloristic interpretation. I mean, Kappa-Minkowski is the algebra of Kappa-Minkowski is generated in, let's say, 2 dimensions by 2 operators, T and Q, that you interpret as time and position, with commutation relation given by T commutated with Q. This is proportional to Q. There is a proportionality constant. Okay, up to replacing real by complex numbers, this is the same example that is on top. The quotient map is the one sending Q to 0. So the projection, let's say the pullback of the inclusion of the horizontal line of the timeline. And so a fancy way to interpret this counterexample is by saying that time is not a non-commutative submanifold of Kappa-Minkowski. I don't think that people studying, let's say, physical application, I don't think they care about this, but still, since I used to work also on this kind of stuff, okay, it was something nice to mention. Okay, from this counterexample, since one is looking for maybe some kind of no-go theorem or some kind of abstraction, we will see that there are abstractions that one can, I mean, when working with formal deformation. More generally, it's not easy to come up with some general no-go theorem. So at some point, the idea was, okay, what is the property of this counterexample? Well, one property of this counterexample, one obvious property is that the big algebra A has a trivial center, while the quotient algebra B, well, this is commutative, so the center is not at all trivial, is the wall B. So the quotient map pi is not surjective on centers, and at some point I thought, okay, maybe this has something to do with the submanifold algebra property. Why this? Because, okay, pi star is a module map over the center. I mean, the target space is a module over the center of B. The domain is a module over the center of A, and this is a module map that covers the restriction of pi to the center. So in the example on, that we have in this slide, pi restricted to the center is not surjective, and also pi star is not surjective. So maybe the non-surjectivity of one maybe has something to do with the non-surjectivity of the other. Unfortunately, this is not true. And you can provide that there is an obvious example where pi is not surjective on centers, but still you have a co-embedding. So on derivations, it is surjective. And this obvious example is given by free algebras. Okay. So if A is the algebra freely generated by any set S, then you can prove that any quotient map from A to B, whatever is B, is a co-embedding. If you want, you can think of this as the free analog of the polynomial example that we saw before. So in the commutative case, we say that every quotient algebra of polynomials in x1, xn is a submanifold algebra. Here, you forget about commutation relations. You have this free algebra, and still this is true. A particular instance of this example is something that was already in Thierry Masson's paper. He gave the example where A is the tensor algebra over some vector space. And the quotient algebra, if I remember, was the symmetric algebra. So he considered the map from tensors to the symmetric algebra. So this is some kind of generalization. Whenever on top you have a free algebra, actually any quotient map is a co-embedding. Let's see. Okay, maybe I can say a few words about this. It should be fine. So how do you prove this? This is quite similar to well-known proofs that you have in the commutative case. You don't have color differentials, but almost. So suppose pi is surjective. D is a derivation of the quotient algebra, and call C the subalgebra of matrices with elements in A that has this form. So 0 below is triangular, and on the diagonal it has the two elements are equal. Then if you take any generator X, so in S, there exists an element delta X of the algebra such that was image was such that pi of delta X is the derivation acting on pi of X. Then what you can do? Well, you use several times the universal property of the algebra A. You have a map F from generators to C, given by f of X is X delta X, X0. This has a unique extension to a map F tilde from A to C. This F tilde, again using universal property, you prove that on the diagonal should be the identity. So F tilde of A is A, D tilde of A is 0A for some map D tilde. And the fact that F tilde is a homomorphism implies that D tilde is a derivation. And the last thing that you do is that this derivation is the lift you were looking for. So since pi F tilde of X is equal to F pi of X for every generator X, it implies, again, by the universal property that pi D tilde is a D pi. So you have a lift of the derivation you were looking for. Okay, so about what I was saying before, the relation between surjectivity of pi star and surjectivity of the map within centers. Now we can construct a counterexample to this kind of conjecture. So take A, the free algebra with two generators X and Y, B, the algebra of polynomials in X and Y, the obvious quotient map. So pi, again, is not surjective on centers because one center is trivial and the other is the whole algebra. It's not surjective on the centers, but still pi is a co-embedding because of the proposition that is written on top, because every quotient algebra of A is a submanifold algebra. So there is not such a nice theorem, I could not find some kind of simple characterization of co-embeddings using centers. Okay, now we pass to the part where you can actually prove stuff. And so we pass to formal deformations. From now on, smooth functions will be complex. So let's change the notations. Since I want to use you can work with real functions, but I want to use a physicist's conventions. So C infinity of M now are complex valued smooth functions. Okay. So I think I have time even to recall what is a star product, even if probably everybody knows. So given a Poisson manifold M, so by a star product, we mean a multiplication, a bilinear associative binary operation on a power series of smooth functions. So something written like this, for given two functions f and g, the star product is a power series in h bar, my formal parameter, with coefficients given by some bk of f and g, functions of f and g. We assume that each bk is a bidifferential operator. And at order 0, you want to get pointwise multiplication. At order 1, the antisymmetric part of the star product, I want to get up to a constant, I want to get the Poisson bracket. So here I'm using, there is an I, I'm using, let's say, physicist convention. I mean, you can also do it without the I. And this is why I'm using complex functions, just only for this reason. Also, another condition is that the constant function 1 you want that is a neutral element for the star product. So you get another set of condition giving you this. Okay, we can assume you don't lose the generality if you assume that B1, the first order part, is antisymmetric, because we know that every star product is equivalent in a suitable sense to one with B1 antisymmetric. And from now on, I will assume this. I will assume that B1 is antisymmetric. Otherwise, some things that I'm going to say are not true. If you take your power series and you stop at some finite order R, and you work over the ring, instead of formal power series, you take polynomials in H bar over H bar to the power R plus 1, you get the definition of order R deformation. This is a nice framework, again, as I said, to study the lifting property of derivations, because you can give geometric interpretation to everything, and you can use basically all of the tools of differential geometry. I mean, also sister algebras are a very nice framework, but in that case, everything is known. There is nothing new after. I mean, besides, it was proved by Pedersen that in the severable case, every derivation can be lifted. So there is not much more one can say. Okay, in the case of formal deformations, the derivations that I'm going to consider are those that we call H-linear. I see popping up some, I think it's somebody is writing in chat questions.
Yeah, yeah. So I'm reading the question to you now.
Yes.
Is the Moyal product a special case?
Yes, Moyal product, kappa Minkowski, if you define in the sense of formal power series, I mean, is a special case of star product. Then we are going to see if it is a special case of submanifold algebra of something. Okay, sorry for not reading the other questions, but I have the first time.
No, I'll do it for you.
Okay, but in any case, at the end, I think there will be still time for questions.
Yeah, there is not perfectly well in time.
Okay, so the derivations that I'm going to consider are formal power series of differential operators on M. These are the ones that we call H-linear, and these are the only one that I'm going to consider. So from now on, by their A, I mean not all the derivations, but only the H-linear ones. So what is one which is not H-linear? For example, the one that we denote by H bar D over the H bar, this that we call, I don't know, formal Euler vector field maybe, which is something that is used, is interesting, but this is not a derivation that I'm going to consider. So
maybe you should denote it not as der of A, but der, say, subscript H bar of A.
Yes, this is true, but then I should rewrite all the definition that I gave before. Because, I mean, the map pi star, the push forward is no longer on all derivations, but only on these H-linear ones and so on. So I think it's easier to change notations. And everything I said before, all the definitions are still valid for this subset of subclass of derivations. Okay. So what are H-linear derivations? Well, at first order, they are something very nice. If you are looking at a first order deformation, and I put epsilon instead of H bar just to emphasize this, then a derivation is just a sum, d0 plus epsilon d1, where d1 is a derivation of C-infinity of M, so a vector field, global smooth vector field. And d0 is also a global smooth vector field, but it should also preserve the Poisson bracket. So it is a Poisson vector field. This is true only if at first order you assume your star product is antisymmetric, otherwise it is not true. But I'm assuming this exactly for this reason. So at first order, a derivation is a Poisson vector field plus an arbitrary vector field. In the symplectic case, this is almost true at all orders. And okay, so this is something I'm going to recall some construction by Cahen, Gut, and maybe others. So this is something well known, but since we have a bit of time. So if M is a symplectic manifold, we denote by this symbol the set of formal symplectic vector fields on M. By definition, they are formal power series where each term is a symplectic vector field on the manifold. So symplectic vector field means a global smooth vector field which preserves the symplectic form. You can cover a manifold by contractible open subsets. On any contractible set, a vector field on a contractible set is Hamiltonian. So each of these xk, if you restrict it to U, it will be Hamiltonian. It will be given by Poisson bracket with some local smooth function defined on U that is denoted by FKU. So locally, formal vector fields are of this form. Now you can take the collection of these maps defined for each U of your covering, and the collection of these functions gives a well-defined global function that I denote by dg. You can check that this is globally well-defined, and the map that you get, this dg is defined in the following way. Its restriction to U is you take the same functions fku. Instead of the Poisson bracket, you take the star commutator and you put the proper coefficient in front. This formal power series give you some functions on U, function on U that I call dg restricted to U. The notation makes sense because this is really the restriction of a global smooth function. What you get, you can prove that you get a well-defined derivation of the star product, and this derivation it is independent on the choice of these functions. It only depends on the formal vector field. So what was proved by Gut and Raunsley is that every H-linear derivation of a symplectic star product is indeed of this form. It comes from such a construction.
So from a Hamiltonian vector field, right?
Formal symplectic vector field.
Sorry, formal symplectic.
Yes, only locally they are Hamiltonian. Then what happens if your manifold is contractible, or if H1 of your manifold is 0? Well, in this case, every symplectic vector field indeed is Hamiltonian. And so in this case, you can prove that every derivation is almost inner. So it's given by the star commutator with some some power series of global smooth functions. So f is not a function, it's a power series, but is global smooth functions. And you have a coefficient in front because in the star commutator you start from order 1. So, and if you put 1 over h bar, you start from order 0. So if h1 of m is 0, then every derivation is of this form, and we say that is essentially inner. So as you can guess, like in the general case, when you have only essentially inner derivations in a quotient algebra, so your push forward of derivations is surjective on essentially inner derivations. And so if the quotient algebra is only essentially inner derivation, still it is a submanifold algebra. You just add the word essentially to what we said before, basically. Okay, so let's go back to submanifold, to quotients and submanifold algebra. So suppose you have now two formal deformations of Poisson manifolds M and N. We come back to the general case of Poisson manifolds. You have a surjective algebra homomorphism, and not the most general one. I want a formal power series of pi k, where each pi k is a map sending functions to formal, sending functions to functions. Okay, what can we say about this map? So, well, first of all, you can check that pi 0, each of these pi k is the pullback of a smooth map from N to M, and at order 0, pi 0 is a Poisson map. The property of being a homomorphism for the star product tells you that pi 0 respects the Poisson bracket. Pi surjective, like it always happens with formal deformations, there are properties that it is enough that they hold at order 0. So pi surjective if and only if the 0 order part is surjective, but we know that pi 0 surjective means that f is a proper embedding. So pi 0 surjective means F is proper embedding. So the image of F is an embedded, closed embedded submanifold, not only a submanifold, but a Poisson submanifold because of the first property. So, okay, so if you have a quotient map like this, you know already that up to an identification, sorry, this is f of n, this is a typo, it's not m. Up to identification of n with its image inside the big manifold, here n will be a Poisson submanifold of M. Okay, now if you have a quotient algebra, you have a Poisson submanifold. What about the opposite? Suppose you have a submanifold. Can you restrict the Poisson bracket, star product, and so on? And okay, of course, this is not always true. Suppose M is a Poisson manifold and S a submanifold, not Poisson, just a submanifold closed and embedded, and call J the vanishing ideal. Then what you can say is that if J is a Poisson ideal, meaning that the Poisson bracket with J stays in J, then, well, you can restrict the Poisson bracket to S and you get a Poisson submanifold. And you can observe that the condition of J of being a Poisson ideal is equivalent to the condition that all Hamiltonian vector fields can be projected, belong to what I denoted before as their pi, where pi here is the pullback of the inclusion of the algebra. Okay. So if J is not only a Poisson ideal, but is ideal in ideal, if you have a star product on M and J is an ideal for this star product, well, then in this case, we say that the star product is tangential to the Poisson submanifold, and you get a star product on S by restriction. So in this case, what you get is that the pullback of the inclusion of S into M gives you a surjective homomorphism of formal deformations from functions on M to functions on S, and a special one that has only the order 0 part. So pi is the pullback of the inclusion, and so is just pi 0. You don't have higher order terms. Okay, so an example of quotient algebras in these formal settings is given by Poisson manifold and submanifolds equipped with a tangential star product. Now, is this a co-embedding? Is this a submanifold algebra, or on top? Is this, if it is surjective, is it always a co-embedding? Now, here there are obstructions that one can prove. Let me first give an example. So sorry, back one slide. I want to give an example of a tangential star product that indeed gives you a co-embedding. So this is a nice example that was, it is in a paper by Bieliawski, Borderman, Guth-Waldman. And there is really here, there is nothing more than what is in this paper. It's just rephrasing stuff. So take G a compact connected Lie group, G star is the dual of the Lie algebra, O capital O is a regular coadjoint orbit. Then on G star you have a special star product which is called the Becker-Campbell-Hausdorff star product. So what they proved in this paper is that there exists a star product on the conjoint orbit, and there exists a power series of differential operators on G star, G invariant differential operators, such that the pullback of the inclusion of the conjoint orbit composed with this power series gives you a quotient map of formal deformations. So a map from the formal deformation of G star with BCH star product to the formal deformation of the coadjoint orbit. Let me skip, you can adjust things so that you can change the first star product so that this T disappeared, not important. The important point is that if you call pi this map, this is not only a quotient map, but it is a surjective also on derivations. And again, for in some sense trivial reasons, meaning that if you have a compact connected Lie group, we know that coadjoint orbits are simply connected. So H1 is 0. All derivations of the quotient algebra are essentially inner, and then automatically you have a submanifold algebra. So cojoint orbits are examples with this kind of deformation, with this star product that is in this paper by the four mentioned. So these deformations of cojoint orbits are examples of non-commutative submanifolds of G star. Okay, let's pass to last part to the this theorem with abstractions for co-embeddings. And so let us assume in previous example you can reparameterize things so that your quotient map pi has only the order 0 term. So let's study this example. Let's consider a quotient map of formal deformations, A, capital A and capital B as before, where M is a Poisson manifold, S is a Poisson submanifold, and pi is the pullback of the inclusion of S to M. At least in the case when S is symplectic, it is not true that every derivation is inner, but it is almost true. At least locally, they are inner derivations. So one could think that every such quotient map is a co-embedding. This is not true, and counterexample can be constructed using this proposition. First part, the first claim is that in the Poisson case, if there exists a Poisson vector field on S that cannot be extended to a Poisson vector field on M, then this map is not a co-embedding, is not surjective on derivations. So of course, if you have a Poisson vector field on S, you can extend it to a vector field on M because it's a closed submanifold, but this maybe will not be Poisson. You want to find an extension that is still Poisson. And the first part is something that you can expect because of the remark that I presented before, that at 0 order derivations are just Poisson vector fields. If M and S are both symplectic, then you can prove that the morphism pi induces a morphism from H1 of M to H1 of S. And if pi is a co-embedding, then this morphism should be surjective. Morphism here is just, I mean, linear map. Why this is true? Here you just identify in the symplectic case, H1 is, you can identify it with the quotient of symplectic by Hamiltonian vector fields. So that are particular kinds of derivations. So if pi is a co-embedding, you have, it induces a surjective map from H1 to H1. As a consequence, as a corollary, if H1 of M is 0, then your map pi is a co-embedding if and only if also H1 of S is equal to 0. And now I can use last property to produce a counterexample. I mean, not to the proposition that I hope I am not presenting the proof because there is no time, but it should be correct, I hope. I'm going to present an example of quotient algebra in this formal framework, which is not a submanifold algebra using this, actually a class of example. So what we can do is the following. So I want to construct an example of a symplectic submanifold of a manifold M, such that H1 of M is 0, but H1 of S is not 0. And okay, this is the obvious thing to do is that you take as M a complex projective space with standard symplectic structure, and you take as S any complex submanifold. Complex submanifolds of this M are also symplectic submanifolds. And you have to find now a complex submanifold with a non-vanishing H1. So take, for example, any Riemann surface with genus not 0, and then you are done. So if you have a deformation of a Riemann surface and the deformation of projective spaces, and the first is a quotient of the second, you can be sure that this quotient will not be a submanifold algebra. Okay. But there is an easier example that I want to present because still is always the same example in different in a different framework, actually non-example. So an example of quotient which is not a submanifold algebra. So take M equal to R2. Take as star product this kind of Moyal product constructed with the following two commuting derivations. The first derivation is d over dx, and the second is y d over dy. So you take these two derivations, they commute. The exponential of this bivector gives you a star product. And as a submanifold, okay, and this is not a symplectic example. The Poisson structure on M is the wedge product of x and y, so it vanishes for y equal to 0. So it's not a symplectic counterexample, it's a Poisson. As x, you can take the horizontal axis, and this star product is tangential to S simply because it becomes trivial on S, it becomes commutative. For y equal to 0, star is the pointwise product. Then you can consider—
There's a stupid question, if I may. In your definition of tangential,
yes,
you use somehow
tangential means that sorry, tangential means that if you have a function vanishing on S and you take the star product with any other function, the star product still is vanishing on S.
Yeah, so but I'm wondering about the order of taking the star product. Does it matter?
Well, it must be true in both orders. I don't know if this is what I wrote, but
you wrote one order somehow, and this is one.
No, then okay, you have to add the other order. Yes, okay, sorry, no, this is my mistake. Of course, this is non-commutative, so also the other one must be true. And okay, in this case is trivial because okay, I have something, the exponential of something antisymmetric. Okay. And so now on the real line, you can take always the same counterexample. You take this kind of Euler vector field. This cannot be extended to a Poisson vector field on M. It is not difficult to check. You can explicitly compute everything. So since there is a Poisson vector field on S that cannot be extended to Poisson vector field on M, previous theorem tells you that you have a quotient algebra which is not a submanifold algebra. This is a nice example because the quotient is commutative. You have the real line as a quotient of some non-commutative deformation of the plane. Then what is this non-commutative deformation? If you take x and y and compute the star commutator, this is proportional to y. So it is again the same kind of example in a different context. Of course, it doesn't matter this commutation relation. If you take polynomials or smooth functions of formal deformation, of course, you have to repeat the proof. I mean, you have different algebras. Okay, so I think I'm going to close here. There is a last part that I'm going to skip. There are more general examples that I'm going only to mention related to coisotropic reductions. So more general example of quotients of formal deformation, and for some of these examples, you can prove that the quotient algebra is a submanifold algebra. And if somebody is interested, this is in my paper and or also on this slide that I think you will be able to download. And so this is a framework where you can produce examples, but I don't have general theorems. So let me finish only with some references. So first of all, there are recent papers about submanifold algebras in some sense by Gaetano Fiore, Thomas Weber, and Davide Franco, where they study submanifold algebras in the framework of Drinfeld twist, we can say. So formal deformations of closed embedded submanifold of certain type induced by Drinfeld twist. There are, I want to mention also some interesting papers. There is one by Catano and Felder where they give a relative version of Kontsevich formality theorem where they deform exactly, I mean, it is more general, but this construction in particular works for deformations of pairs of Poisson manifolds and coisotropic submanifolds. So this could be a framework where one can study this property of lifting derivations. And there are more geometric examples that one could study. So for example, instead of isotrophic reductions in the algebraic sense that was in the slide that I skipped, you can study a more geometric version of the reduction coming from an action of a Poisson-Lie group on a Poisson manifold. Or if you want, you could replace Poisson manifolds with Jacobi manifolds. And this is another framework where one can perform this kind of study. Okay, I'm going to finish here. Thank you very much for staying with me this long.
Okay, thank you very much. So I'm clapping my hands.
Yeah.
Did it work?
Okay.
I'm trying to
there is a button, but I don't know how it works.
Reactions. Can you see it? I don't know.
I see the button. Yes, I see that somebody has a hand.
Yeah.
Okay.
I'm pressing this clapping hand. And anyway, thank you very much for a very interesting talk. And now we can have more questions, please. Anybody, any questions?
I guess I have a sort of obvious question. Have you looked at any of this for smooth non-commutative tori, or even more generally the Kunlandi deformations of manifolds?
No, this is a very nice question. I mean, I thought about it, of course, but no, I didn't. I had mainly because I had no time, and also, yeah, I mean, the torus would be very interesting. Yeah, I think probably, I'm sure that something can be done. If one is lucky, maybe there is some difference between rational and irrational case. But I didn't do it, no. It is very interesting. This is something that somebody should do. I don't think, I don't know, Thierry, I don't know if he's online. Since he's the one who proposed the definition, I don't know if he tried to study the non-commutative torus.
Yes, I'm online.
Yeah.
Thank you for your talk. No, I have not tried to pursue in that direction. So you are the first one to consider that after me, I think.
I think it is possible that those studying Riemannian embeddings, that they did something about the non-commutative torus. I'm not sure, but it is possible. Okay, it is different. It is...
I guess first problem is when it's simple, right? Irrational torus is simple. So there are not that many quotients.
Yes. So maybe you mean you should think of the torus as quotient of something else?
If anything, yes,
but it is simple only for irrational theta, right? I mean,
so,
okay, rational, okay, maybe is not that interesting, the rational case. Well, the rational is almost commutative. So in the rational case, at least, I mean, if you think of the rational non-commutative torus as a bundle of matrix algebras over the standard torus, then fibers are non-commutative submanifolds still because you have finite dimensional C-star algebras. Now, the irrational case, yeah, it could be interesting to see if the torus is a quotient of Moyal, for example, non-formal Moyal. If it is no, it's not a quotient, it's a subalgebra, so no.
Subalgebra.
Yeah. Yeah, one should
for higher
think
dimension,
about it.
You can certainly get non-simple and yet quite non-commutative.
Yeah, and in any case, there are theta deformations of other manifolds. One can consider deformed spheres. Well, if there is a twist, I think that things should work, even if it is not really formal twist, but something more complicated. Yeah.
Anybody else?
I have one question.
Go ahead, Andre.
So, Francesco, very nice talk. I have one question regarding, the difference. Can you somehow see the difference, or can you see the examples of something which in the classical case is not a manifold or a submanifold, like an orbifold rather, but then in non-commutative case, it will be a manifold, it will be a submanifold. Is there anything like that? I mean, I
don't know, I didn't look at orbifolds, but this example, the cross, this is an example because you have a double point. The origin is, so it is not locally Euclidean around the origin. You cannot put any chart, smooth chart on the cross around the origin. So that is not a smooth manifold or a topological manifold in any way, but it is a non-commutative submanifold of the plane.
Okay, so then in a non-commutative sense, it would be like that. You know, the background of the question is that, for instance, if you look for equations of the tori, non-commutative tori, then
yes.
If in a classical case, there will be some orbifolds, so they would have some, you know, singular points, but then suddenly in a non-commutative case, sometimes even in the rational case, I mean, they look like behaving a little bit, I mean, on the algebraic level, on the level of smoothness, and if Tomek is listening, then
yeah, this is I understand what you mean. I remember in Thomas' paper the case of teardrops, right? That they are not a smooth submanifold of R3 in the commutative case, but then when you deform them, they become in some sense smooth.
Exactly. These are just the examples.
Yeah. So that could be, that was another example I wanted to study, but then I mean there are thousands of examples, so at some point you have to stop and publish and get paid, let's say. But that is a nice example, yeah.
Okay, something to look into it, yeah. Okay, thanks.
Yeah.
I understand that, Ali, you have a question because you raised your hand. So if you have a question, go ahead.
Yes, my question is that is the Kalkin algebra is a co-embedded submanifold of the operator algebra of BH, because the Kalkin algebra is the quotient of operator algebra, but is it obvious? Is it an obvious question that it is a co-embedded algebra?
Well, if I mean, if you take a separable Hilbert space, then it is a separable sister algebra, right? I mean, if you have a
Kalkin algebra.
No, sorry, the Kalkin algebra, no.
The Kalkin algebra is the quotient of the operator algebra.
By the compacts, yes.
The operator algebra divided by compact operator.
Yeah, so now I don't remember, is it separable? If it is separable, then you are done.
No, it's not.
It's not, then I don't know. Maybe it is this counterexample. It is possible that is related to this counterexample by Kedison Ringrose. I don't remember.
Do we have some? Yes. Do we have some information about the derivation of the Kalkin algebra? Are all derivation inner, or there are some non-inner derivation of the Kalkin algebra?
Yeah, I don't know. I mean, this is a very interesting question, but I don't know the answer. It is possible that is something known, but maybe to Mark, I don't know if Mark knows something more.
Yes, I see. Thank you.
No.
Thank you.
Okay.
All right. Any other questions, please?
Yes, I have maybe two questions.
Mm-hmm.
The first question is about something which worries me a little bit. Do you have a notion of a manifold?
No, he doesn't.
No, of course, no.
So in many of your examples or non-examples, you are mixing spaces which or algebras corresponding to some non-submanifolds in the usual sense, or something which has different algebraic properties comparing with algebras of smooth functions on manifolds.
Yeah. I mean,
no. a lot of these non-examples is a sign of some misnomer of this notion.
Well, let's say the following. So let's see the commutative counterexample. Let's say the real line as a subset of the cross, let's say.
Mm-hmm.
Okay, I have a notion, okay, but then in this framework, non-commutative submanifold is just a name. I mean, we are studying when a quotient algebra has this lifting property for derivation. Then, okay, we can call it submanifold algebra, it's just a name. Let's think of the cross as a subset of R2. R2 is a manifold, at least this one. the cross has this property. So I would say that is a non-commutative submanifold in this sense. So it is quite a good example in the sense that it is something that you would call non-commutative submanifold over R2, and then in particular non-commutative manifold. There is of course no manifold structure, there is no Dirac operator, or so I have only algebras at this level. But if you accept that the cross is some kind of non-commutative submanifold, then the real line, the horizontal line, is not a non-commutative submanifold of the cross, and in this sense it is some kind of geometric example. But it is true. So I mean, there is no notion of non-commutative manifold, but still this is just a name. I mean, you can say that a spectral triple describes a non-commutative manifold. The notion of a non-commutative submanifold, well, we call it actually co-embedding or submanifold algebra. This is a mathematical definition. So after all, is a name. And the question, I mean, it is true that I don't have any example of quotient algebra of infinity of M, which is not a submanifold algebra. To find a non-example, here I have to put a smooth function on the cross, which is not a manifold. So if here you have a manifold, this is I mean, for me it's an open question. Maybe there is a simple non-example, but I don't know it. But for me, it's an open question. Suppose here you have smooth function on a manifold, not just a subset of a manifold. And B is a quotient algebra, so yeah, and can you find the quotient algebra which is not a submanifold algebra? So this was the question. And this I don't know.
Yes, so if you are talking about examples which are algebraic, then there are plenty of names separating these cases.
No, but I mean, I know in the algebraic case, I mean, still one non-example is given by the ring of coordinates functions on the cross.
No. I'm talking about the names used for these subspaces. So they, for instance, your dual numbers example is about non-reduced subscheme. Some other example, the cross is a subvariety, not submanifold.
Yeah, sure.
So in your terminology, everything degenerates to one notion, which doesn't work well in all situations. And yeah, so this was first question. The second question is about this Poisson case.
Yes.
Do you assume that your B1 is anti-symmetric when you define your tangential star product?
So I assume that my B1 is antisymmetric because other.
Okay.
I mean, I'm assuming always that is antisymmetric. Now, the places where you need it is the fact that at order 0 derivation is a Poisson vector field. This is true if B1 is antisymmetric, but you can always pass to this case with an equivalence. I mean, and another thing that is true is this characterization in terms of formal symplectic vector fields of derivations. This is true if B1 is antisymmetric. But I mean, in the general case, you just have to reparameterize things. It's not a big difference. So every star product is equivalent to one which has B1 antisymmetric.
Yes, but this relation between tangentiality of this star product and
well, also, I mean, also this, the fact that pi 0 is the pullback of a Poisson map, also this is because B1 is antisymmetric. Otherwise, it will be, I guess, the composition of a Poisson map with some other canonical map or something. No, but this algebraic part, I think you don't need B1 antisymmetric. This is, I mean, you have a star product, but you can do it for any algebra. You have a product on a big algebra, a vector subspace. Here, the star product is called a tangential if your vector subspace J is an ideal in the standard sense. Okay, there is one property missing. Okay, also F star J, as Piotr said, should be in J. But this is just algebraic. You don't even need a star product, I would say.
By the way, Francesco, please remember to send me the slides after you correct the typos.
Yes, of course. I think also in the paper there is only one side of the, but okay, the paper now is too late to to change it.
So Tomek, are you happy with the answers?
Yes, but then the last answer.
So no, about, I mean, of course,
opportunity to ask another question.
Yes.
So, do you have an idea what could be a smoothness condition for Poisson manifolds in the sense of extension of derivations?
Well, okay, this is a difficult question. A smoothness condition, you mean you have some kind of quotient algebra and you want to a property that tells you that in some sense the quotient is a deformation of, I don't know, these are always smooth deformations of smooth manifolds. So
yes, but they are smooth as usual manifolds. But
yes.
What would be the formation of this condition? For instance, is a condition of a constant rank of a Poisson vector an analog of this Poisson kind of smoothness? A good candidate for is a symplectic manifold smooth always in this sense?
I mean, here smoothness refers to the property of something being a submanifold of something else. I use smoothness in this sense. So I don't know if this is what you mean, if you can characterize this property of lifting derivations in terms of properties of the rank of the Poisson bivector or something like that. Well, in any case, I mean, unfortunately, I don't have an answer. I mean, the only thing, I mean, basically, besides examples, these abstractions are the only things I can say about formal deformations. I mean, there are many ways one can define smoothness. I mean, there is a notion of smooth algebra. This is, I don't know if this is what you are referring to. If the formal
both smooth algebras and smooth mappings between these algebras.
Yeah, I'm not sure. Look, I mean, I'm not sure if these algebras maybe are always smooth in this algebraic sense, but I don't know. It is not something that that I studied. So
I'm asking because classical submanifold can be regarded as a regular closed immersion.
Yeah, I mean, what you can say is, for example, for algebraic deformations, I mean, what is known in the example of coordinate ring of an algebraic set. So in that case, for example, you can characterize smoothness in terms of derivations. Like if the Lie algebra of derivations is simple, then the algebraic set is a smooth submanifold, or you have something like this. For formal deformations, I don't know if there is some way to, I don't know, what are the results, if there is something to say.
Okay, thank you.
I'd like to follow briefly on Tomek's first question.
Yes.
So you of course know, everybody knows the celebrated reconstruction theorem, where you finally have some conditions on the spectral triple that determine that you are really talking a manifold and not an orbifold or something else. It's a very tough theorem.
Yeah.
And have you at least thought of cooking up the notion of a submanifold, but in this spirit of a reconstruction theorem? So you say, aha, so I have a quotient of my algebras, and I call this quotient algebra a submanifold algebra, if and only if, and then you see in these all the structure which is from a spectral triple passes to this quotient algebra, so that again in the commutative case by the reconstruction theorem you are guaranteed that you are talking a submanifold.
Well, I mean, depends on what you mean by this question. I mean, of course, I've thought about it, not very much, but meaning that I mean, in that case, you have a more structure, not just a manifold. You have a Riemannian manifold. So
okay, yeah, okay, sure.
So it is possible that the other framework there is a different definition related to generalization of isometric embedding of Riemannian manifolds, it is possible that in that framework you can distinguish between orbifolds and manifolds in the reconstruction theorem, for example. But I mean, I don't know this very well, this work of Arnlind and so on Riemannian, non-commutative Riemannian embedding, so I cannot say much.
Okay, thank you very much.
Can I make a comment, small comment? It's Ludwig.
Sure, hello, Ludwig. Make a small, big, or medium comment, whatever you want.
No, small one. I think, well, I think it's okay, the reconstruction. I mean, you mean Alan Kohn reconstruction theorem, I understand, right? So their objects are more or less under control, I would say, but I think we are very far from morphisms between objects. So I don't think what should be maps between them, embeddings and things like that. So.
No, this is true.
So what is a category of spectral treatment?
Yes, that's right.
Yeah. But here it's something very special. I mean, it just takes quotient. So your morphism is canonical in a way. It's just a quotient map. And you're asking about the properties of your target algebra, the quotient algebra. So I agree. This is a big problem in using spectral triples, that it's so non-functorial. Yeah, we might have a reconstruction theorem for a manifold, but I'm not sure whether we have a reconstruction theorem about a smooth function from a manifold to a manifold.
Okay.
Yeah, but this was a very good comment. Okay, so if there are no other questions or comments or complaints or suggestions.
Could I ask the last question?
Okay.
From me, at least.
Yeah.
In the dual situation, when you consider submersions instead of smooth embeddings,
yes,
the problem of extension of derivation plays a role.
The problem of?
The problem, you can extend derivations.
Yes.
Okay.
Okay.
And then the problems of abstractions, of classification, reduces to Hochschild cohomology, in which inner derivations are regarded to be trivial.
Yeah.
Do you have in your situation, when you allow these inner derivations to be non-trivial, do you have some cohomology theory related to these abstractions, to the problem of this lifting and so on and so forth?
Okay, for submanifolds, let's say this kind of submanifold algebras, the only abstraction that I have is this for formal deformations, where the cohomology is the standard one. Then in general, well, you can associate to this exact sequence. So, I mean, this is already in, where is the exact sequence? In theories paper. If you have an exact sequence like this of algebras, then you can pass to some exact sequence in some kind of modified Hochschild cohomology, which is not right exact. You can rephrase things in cohomological terms, but I don't have any theorem saying, okay, if this class in Hochschild cohomology is not 0, then is not a co-embedding or something like this. I try to think about this, but there is no obvious, at least to me, obvious abstraction in terms of cohomology. I mean, this pi star, in some sense, you can think of this as, yes, as the problem of when already at the level of Hochschild 1 cocycles, if this sequence becomes something that is exact only on the left, co-embedding means that the sequence is exact also in the last, you have also last arrow. So you can rephrase this saying that you get a short exact sequence for Hochschild 1 cocycles, but is, I mean, is just rephrasing the same stuff. It's not nothing new.
Okay.
Yeah.
So since it was declared the last question, let's make it so. Thank you very much, Francesco, for your beautiful talk. I ask my fellow co-organizers to remain online so that we talk a little bit. And I thank everybody else. I stop recording and see you next week.